session on universities collaboration. I'm your host, Miriam Wester, and I'm excited to be talking with two distinguished academics as they give a brief overview of the projects that they are working with us on. The first project we will be discussing is one that has been running for just over a year now, called Eclipse Resistant Network Overlays for Fast Data Dissemination. The principal investigator on this project is Spyros Vogaris. Following that, I will be talking to Professor David Say from Stanford University about a new project that we're just embarking on. So, to get the conversation started, Spyros, could you please introduce yourself to our audience and tell us a little bit about the project?
Hello, and thanks for inviting us. I'm Spyros Vogaris. I'm assistant professor at the Informatics Department of the Athens University of Economics and Business in Greece. And we've been working for a bit over a year, as you said, on this project, focusing on the networking aspects of Cardano, more specifically on catering for a dependable network overlay topology, which is able to guarantee the timely dissemination of newly generated blocks across all participants of the Cardano network.
Thank you, Spyros, for the short introduction. I was wondering, could you maybe say a bit more about the research questions that you are trying to answer?
Oh, certainly. Let's take a quick look at the heart of Cardano, because at the heart of Cardano, the Cardano network, lies a delegated proof-of-stake mechanism widely known as Uroboros. So in Uroboros, blocks are being generated every few seconds by a mechanism selecting nodes at random at various parts of the network using probabilities proportional to their state, to nodes' state. So what's crucial to Uroboros security is that no one in the network can be able to know which nodes are going to be generating the upcoming blocks, which nodes will be generating future blocks. Although this is a very important, very crucial, as I mentioned, design choice for the security aspects to prevent attacks to nodes generating future blocks, it makes things quite challenging for the networking layer. Why? Why is that? Well, simply because, as we know, in all blockchains, to generate one block, you definitely need to know the previous block. A node generating a block has to be in possession of the previous block, has to have validated it, and has to include the previous block's hash. Now, in Cardano, when a block is generated, apparently it has to be shipped to the next node, to the node that's going to generate the next block. However, since no one knows who that node is, essentially this block, any newly generated block, has to be disseminated to the entire network, to all nodes of the network, at the same level of timely urgency. So that makes it very important, makes it crucial to have a network, a very fast network, and very fast topology organization to disseminate new blocks very fast to all participants. So our project has been built and it has been orchestrated around three main pillars. The first pillar has been on identifying the optimal organization of the topology, like who knows whom. When you get hold of a new block, whom should you forward it to, in order to maximize dissemination speed across the whole network. This is essentially a peer-to-peer domain. It's a peer-to-peer research. Okay, so having found what is this first pillar, the optimal overlay to disseminate blocks, the second pillar is figuring out how nodes can self-organize themselves into that target overlay, into this target topology. And that is also a peer-to-peer issue of self-organization. And finally, this topology, this self-organizing topology building should be done in a way, that's the third pillar, should be done in a way that prevents malicious nodes, attackers, from exploiting the system. What I mean by that is that when you generate the topology, when you let nodes self-organize into a topology, essentially each node gets to be informed about additional nodes through its neighbors. So if I have a malicious neighbor, and this neighbor helps me to find additional neighbors. If this node is malicious, he's going to give me malicious nodes as suggested new neighbors. And the danger there is that at some point, if all malicious nodes provide me with malicious neighbors, I might at some point find myself surrounded by exclusively malicious nodes, something known very well as the Eclipse attack. I may be eclipsed from the legitimate part of the network. So our third pillar has been on finding ways to impose, to make sure that nodes will be forming a topology abiding strictly by the rules of the proposed protocols, essentially preventing nodes from deviating from the rules and from arbitrarily suggesting malicious neighbors to other nodes. Okay, so these are basically the three pillars: finding the right topology to do dissemination, finding protocols to form this topology in a self-organizing manner, and finally, making sure that nodes have to follow the aforementioned rules without doing anything arbitrarily. That's pretty much a high-level presentation.
Thank you very much, Spiros. That was very clear. I was wondering, would you also maybe like to say something about how because you've been working with us for, like, as I said, over a year now, how you've been engaging not only with our research team, but also how you've been working closely with the engineering and benchmarking teams?
Absolutely, I'd be happy to. Basically, we're having bi-weekly meetings with the IOHK engineering team. That's a very focused team, a very it's a very advanced team. People that have very strong scientific background, but at the same time, they have a very solid intuition and knowledge of what's happening in the real world. So it's ideal for an academic to be in contact, to be in very close collaboration with such a team. So it's really scientific and engineering team combined. And as you mentioned about the benchmarking part, sure, it's that's like people working at the IOHK engineering team have also been benchmarking some testbed network and the real network of Cardano, and they have been sharing with us log files and results, which we are comparing to our simulation results to make sure that we have much more realistic simulations and a more educated conclusions to our research. In addition, we're having those weekly meetings at a higher level, but yes, that's probably not for...
Okay, thank you, Spiros. That sounds fantastic, and I really appreciate you giving us a bird's eye sort of view of the research challenges you've been working on. And I look forward to seeing how it further develops and how the findings are integrated into Cardano. Then now it's my pleasure to announce a new academic partnership with Stanford University. Professor David Say and his team will be working on a project called Verifiable Digital Fountains. David, thank you so much for being with us today to discuss this new exciting project. Could you maybe introduce yourself and say a few words on how this collaboration came about?
Thanks, Miriam, for inviting us here to present our work to this meeting. So my name's David Shea. So I'm a professor at Stanford University. And so I've been working in blockchains for a few years, and I'm very excited to work on this project. So the team members is Kamila Nazarkanova is a second-year PhD student at Stanford, and another student, Joachim Nur, is a fourth-year student. So we have a team right now consisting of me and two students. We may add some more people as the project progresses, but that's the current team.
Thank you very much, David. Can you maybe explain a bit more what verifiable digital fountains are, and maybe also why they might be of importance to Cardano?
Sure. Maybe first a few words about how we get this project collaboration started. So Agelos Kialis, the chief scientist of IOHK, we have been interacting for quite a few years now, because we've been working on similar related research problems. We have had a lot of discussions, more informal. So a few months ago, I approached him and I said, hey, we have some new ideas, new technology that may be useful for IOHK and for Cardano. And I would like to see if we can have a collaboration where we can advance our ideas and maybe have a prototype on Cardano to nothing better than experimenting on a real running network. So that's how the project got started. So what is verifiable digital fountain? So if we take a step back, if we look at a blockchain like Cardano, then Cardano is like the original Bitcoin, where all the data processing, the execution, storage, communication of all data is done by every node in the network. So this is the original Bitcoin model. And that is very good, very secure. But one drawback of that is the scalability. Because everybody has to do a lot of work, it's very hard to scale the network. And I think that's sort of one challenge facing Cardano. And so the idea of verifiable digital fountain is the following, is to roughly, the idea is that you decouple the data, storage, communication, execution, away from the consensus, the heart of the consensus problem. So think about the data is like storing like a fountain in a network. So you have data everywhere. Everybody has a little chunk of the data, not the whole data because you can't store that much. So the data is out there spread out across the whole network. However, it is verifiable in a sense that everyone who needs the data can actually access it by querying a set of nodes to sort of collect the water from the digital fountain. And once you collect enough water, then you can decode and get the information. So that's roughly what verifiable digital fountain means. So about a year ago, we used this idea to be able to design a system we call Disburse Ledger. So a Disburse Ledger is kind of interesting because imagine if you have a communication node, which is like a cell phone. Suppose you are a cell phone running blockchain or running, and then sometimes you have poor connectivity, right? Because you're on a cell phone, like Spiros, for example, a little bit earlier. Sometimes your phone may be not very clear. Sometimes you have very good connectivity when you get to a hotspot. So our system enables you to participate in consensus all the time. However, only when you have good bandwidth, then you can download the data from the digital fountain in order to have the data. But all the time you can continue in participating in the consensus. So that's the system we built. So we're quite excited to see if this idea can be sort of implemented and in the Cardano network, in the Uroboros, as the Spiros just mentioned, the Uroboros protocol, to work in conjunction with the Uroboros protocol. And so that's basically our project. Now, for people a little bit deeper into the blockchain space, this problem is actually a broader part of a broader problem called a data availability problem. So for people who are in blockchain, they may know this term. So I just want to make a connection there. So the data availability problem is a very important problem for scaling blockchains. And actually, several other projects have been working very hard on this problem. Some names that you may have thought of is Lazy Ledger and Polygon. These projects, they all have data availability solutions. However, our solution or our approach is rather different from their approach. Their approach is based on probabilistic algorithms, probabilistic random sampling of information to check data availability. That approach comes from the proof of work history. And the one drawback of that approach is probabilistic. So our approach in the contrast comes from a history from the permissioned world, which is called Verifiable Information Dispersal, VID. People have heard of that. And in that approach, the fact that you have dispersed data, that the data is retrievable, can be actually verifiable through a proof, a certificate. So it's not probabilistic, it's final. And so in some sense, it's like the finality approach versus the probabilistic approach. And so the challenge is to bring this technology from the permission world where there's a fixed number of validators forever, to the Cardano world, the proof of stake world, where you have a dynamic set of validators changing over time. And the stake distribution is being updated continuously. And how to build a system in conjunction with that is sort of one of the big challenges of the project.
That was very, very fascinating, David. Thank you so much for the quick summary of this project that we're going to be embarking on, as we speak. And I think that's all we have time for today. So I want to thank you again, Spiros, for being here with us to tell us a little bit about your work. And as I said, David, thank you very much for your time. And we look forward to further collaboration. Thank you.
Thank you very much.
Thank you very much.